Hi, I'm Andrew Wilson, and welcome back to part 2 of the ICML 2020 tutorial on Bayesian deep learning. In this part, we'll be considering a function space perspective of machine learning. We'll cover Gaussian processes, infinite neural nets, how training a neural net is like learning a kernel, Bayesian nonparametric deep learning, and several other topics. From the function space perspective, the parameters in isolation are entirely divorced from the statistical properties of a model. In part 1, we considered how in regularization, whether or not we want large weights or small weights entirely depends on the parameterization of the function that we're using. Yet we focus most of our modeling efforts on learning parameters W. What we really care about are how those parameters W combine with the functional form f of xw. Ideally, we want to perform inference directly in function space. Let's return to the example that we considered in part 1, where we had a distribution over functions induced by a distribution over parameters in a linear model. We'll consider f of xw equals w0 plus w1x, and we'll place a standard normal distribution over w0 and w1. We can sample from that distribution to get different values of w0 and w1, corresponding to different straight lines with different slopes and intercepts. The gray shade here corresponds to a 95% credible set. 95% of these functions are in that shade. And the solid blue line corresponds to our expectation of this induced distribution over functions. We'll now consider the more general model class, where we have an inner product of a vector of weights w with a vector of basis functions phi. The entries of phi, for example, could be 1, x squared, x cubed, if we're considering a polynomial basis. We could alternatively consider a Fourier basis. This model class is quite general. And we'll place a Gaussian distribution over W with mean 0 for convenience and covariance matrix sigma W. Now I'd like you to pause the video for a second and see if you can derive the moments of the induced distribution over functions given by equations 38 and 39. Now, all of the randomness in this model is coming from the distribution over parameters W. So we can pull phi out of the expectation, it's just deterministic, and we can evaluate the expectation over W, and by definition in this case it's just 0, so the mean of this induced distribution over functions is 0. Now, f of xi and f of xj are two different random variables corresponding to querying our random function at two different input points, xi and xj. So the inputs could be time, spatial locations, whatever is indexing our random function. We can use the definition of covariance and derive the covariance function, also known as the kernel function in this case, as the inner product of phi of xi with phi of xj under sigma w. Now, I'd like you to consider whether there are any higher moments in this induced distribution over functions. In this case, there are no higher moments because we just have a sum of Gaussian random variables in equation 40, and Gaussians are closed under addition. In fact, f of x is a Gaussian process with a mean function m of x and a covariance function, or a kernel, kxx prime, for two arbitrary inputs, x and x prime. In this case, we can actually do inference directly over f of x instead of over parameters w. Formally, a Gaussian process is a collection of random variables, any finite number of which have a joint Gaussian distribution. We can use a Gaussian process to define a prior over functions. This notation here, f of x is distributed as a GP, means that any collection of function values queried at any collection of inputs, x1 up to xn, these could be time, spatial locations, images, etc., has a joint multivariate normal distribution with a mean vector mu defined by the mean function of the Gaussian process and a covariance matrix K defined by the covariance function or kernel of the Gaussian process queried at all possible pairs of inputs, x1 up to xn. In the bottom left panel here, we have samples from our induced distribution over functions. To create these samples, I chose a bunch of input points, a bunch of x's, and then I formed my multivariate normal distribution by building up my mean vector mu, evaluating my mean function, in this case 0, at all the input points that I've chosen, and forming my covariance matrix by querying my kernel at all possible pairs of the inputs. I then sampled from that multivariate normal distribution to get the black dots, the random function values. And then I sampled from exactly that same distribution 2 more times to get the purple curve and the green curve. Here I've just joined the dots together. The gray shade again corresponds to our 95% credible set. And the blue curve here corresponds to our prior mean function, in this case 0 for convenience. In the right panel, I've conditioned on some data denoted by crosses, and I've sampled several posterior functions in black, purple, and green. We also have the posterior mean function in solid blue, which we can use to make point predictions, and the 95% credible set in gray shade. Very importantly, all of the statistical properties of these functions are controlled by our kernel. And in this case, we're using what's called an Rbf kernel, also known as a squared exponential or a Gaussian kernel. This kernel has the functional form a squared times the exponential of the negative Euclidean distance between our 2 inputs, x and x prime, over 2L squared, our length scale. It incorporates the very intuitive inductive bias that functions that are close together in the input space should be more correlated than functions that are far away in the input space. For example, airline passenger numbers in 1951 and 1952 should be more similar than airline passenger numbers in 1951 and 1960. So this is a very natural inductive bias. The extent of the correlations is controlled by the length scale hyperparameter L. If L is very small, the function values become uncorrelated. We just have a white noise process. If L is very large, then the function values become all very correlated. A is the amplitude hyperparameter. If A is large, then the amplitude of these functions will be large. In the top panel here, we have visualization of the entries of our covariance matrix when we have 1D ordered inputs. We can see that there's this strong diagonal band where we have highest covariance, and then the covariances decrease away from that band as we increase distance in the input space. So let's consider the distribution over functions that we get when we have particular settings of our length scale and our amplitude parameters, L0 and A0. Here we have our sample prior functions and our sample posterior functions. Pause the video for a moment and think about whether these sample functions look strange to you in some way, and it might be a little bit subtle. To me, these functions look a bit too wiggly. They're varying a little bit too quickly. They're a bit too complex. The mean shoots back down to the prior mean a bit too fast. So to me, that seems like the length scale is too small. Now let's see what happens as we increase the length scale. Perhaps here we've increased the length scale a bit too much. We see now that the functions look too slowly varying, too simple. They're over-smoothing the data. Let's consider again the marginal likelihood that we considered in part 1 of this tutorial. We can form the marginal likelihood in this case by integrating away our Gaussian process, P of f. The marginal likelihood, again, is the probability that we would generate a data set if we were to sample from this distribution over functions. Now, if we have a very small length scale, we just have a white noise process. So we're going to be able to generate all sorts of different data sets, but they're all going to be pretty different from one another. So if we keep sampling from that distribution over functions, well, we won't see the same thing again. If we have a very large length scale, then this induced distribution over functions is pretty simple. As we saw, everything looks sort of like a straight line. Everything is pretty similar. And so we're not really generating that many data sets with very much probability using that large length scale in red. For a given data set, the marginal likelihood will have an Occam's razor property where it will automatically favor a model of appropriate complexity. This is described very eloquently by David McKay, both in his PhD thesis and in his book on information theory. It's also described in the Gaussian Process for Machine Learning book by Rasmussen and Williams. If we optimize our marginal likelihood with respect to length scale, we get the green fit here, which intuitively has an appropriate level of complexity. If we had to choose between one of these curves, we'd probably choose the green curve. Now, we opened this part of the tutorial by deriving covariance functions from classical weight space models. And then we said, well, let's just use a Gaussian process with an Rbf kernel. Now let's derive where that Rbf kernel comes from. We'll again consider an inner product of weights and basis functions, in this case, not expressed using vector notation. We'll put a Gaussian distribution over our weights, and we'll use as our basis functions Gaussian bumps centered at points Ci, as drawn in this diagram. We can grind through the algebra, revert to the definition of our covariance function, and get our covariance function in equation 55. Now let's consider what happens as we let the number of basis functions, j, go to infinity. We'll want these basis functions to cover the whole real line, so we'll let Cj, the center of the jth basis function, be log j, and C1, the center of the first basis function, be minus log j. If these basis functions are equally distributed, then the difference between the I plus first basis function and ith basis function will be 2 log j over j. So we see that that goes to 0 as j goes to infinity, which is why I used log j for the endpoints. I could have used root j, for instance, but not j. And the expression for the kernel in equation 57 becomes a Riemann sum, an integral, with limits c0 and c infinity, in this case, minus infinity and infinity. We can substitute in our expression for the basis functions and evaluate this integral in closed form and get something that's proportional to the Rbf kernel. Now, this is a very extraordinary result. I'd like you to pause the video and just consider what we've done for a moment. We've actually shown that by thinking from a function space perspective, we can use a model with an infinite number of basis functions using a finite amount of computational resources. So in part one of the talk, I opened with this question about how we might model airline passenger numbers, and I said I'd like to use the 10,000th order polynomial from the 3 choices that we were considering. And you might have wondered, well, carrying this argument to its limit, are we even going to be able to store these models in memory, assuming that we want to use them? And in fact, what we're seeing here is we can use something like an infinite order polynomial. We can use a model that is extraordinarily flexible. In fact, this is a universal approximator, and we can see that by looking at this derivation. If we collapse these basis functions onto point masses, we can have densely dispersed point masses with different heights. But we've also seen that this model can generalize very well. It has very intuitive inductive biases. So we should be very careful not to conflate flexibility with the complexity of our model class. And we should also be very careful not to do parameter counting as a proxy for complexity. Here we're seeing that we can actually use models with an infinite number of parameters that in some sense have fairly simple inductive biases and provide very good generalization. In this diagram where we have all possible data sets on the horizontal axis, we're saying we want to have heavy tails, we want to support all sorts of different data sets, but we also want to have mass in reasonable places. And we can get that, in this case, through the inductive biases of the kernel function. I'd like to add a brief note about the mean function. In this tutorial so far, and in many texts about Gaussian processes, the mean function m of x is often taken to be 0 for notational convenience. But in fact, we can use any deterministic mean function without fundamentally changing the modeling procedure. And it's usually pretty standard to subtract off the empirical mean and then use the 0 mean GP or subtract some kind of deterministic mean function and then add it back later. Also, typically the covariance function or the kernel is really the key object of interest. And there are often degeneracies between specifying the mean and covariance function. in which case often it's typically preferred, therefore, to do the modeling in the covariance function. For example, the kernel function shows up in the Occam factor term we get in the marginal likelihood, a log determinant, but not the mean function. That said, a mean function can be a great way of incorporating scientific inductive biases into a model. There's sometimes a tension between using an interpretable, scientifically motivated model, for example, a model with physically interpretable parameters, and some black box function approximator. In actuality, this is often a false choice. We can often use both in this sense. We can use as our mean function that scientifically motivated model, that parametric approach which has interpretable parameters, and then we can at the same time use our Gaussian process with an Rbf kernel to allow for a non-parametric relaxation around that mean function to account for inevitable model misspecification. So we can really have both. We can use that mean function of whatever other model we would have used to calibrate the inductive biases of our approach, and we can concentrate our distribution of functions as closely or as loosely as we like around that scientific mean function. Interest in Gaussian processes in the machine learning community was triggered by work that Radford Neal was doing on Bayesian neural nets. He really embraces this idea that we should build very flexible models, and accordingly was pursuing the limits of very large Bayesian neural nets. And he showed that as we let the number of hidden units in a Bayesian neural net go to infinity, we get a Gaussian process. Here, let's consider the simple neural net f of x equals a bias plus a sum of a bunch of hidden units with hidden unit weights ui. And with fairly general assumptions, one can show using a central limit theorem argument and not even requiring, for example, that the parameters have Gaussian distributions, that we'll get a Gaussian process in the limit as j goes to infinity. And we can derive the moments of the Gaussian process just as we already have been doing in other examples. We can make particular design choices, like we can let our activation functions be error functions, and we can use a Gaussian prior over our hidden unit weights and derive a neural network kernel in equation 69. Here we have samples from a GP with this neural net kernel. We can see that they're non-stationary, that at a high order, the statistical properties in the center are different than in other regions. Unlike, say, the Rbf kernel, which is translation invariance, it's a very flexible model. It could look different in different parts of space, but in a high order, the statistical properties of the functions in those types of kernels will be similar in different regions of space. So this result, that an infinite neural net converged to a Gaussian process, was very exciting in the machine learning community. And in some cases, it drove the idea that we ought to just use Gaussian processes instead of neural nets. At the time, people were becoming very frustrated by all sorts of design decisions associated with working with neural nets, like how many hidden units do we want? How many hidden layers? What are the activation functions? What optimization procedure are we using? What learning rate schedule are we using with that optimization procedure? And the lack of a principled framework to answer these types of questions. Gaussian processes, by contrast, were very simple and interpretable and flexible, and you could write the same 10 lines of code and get the same answer anywhere in the world. Now, David McKay was a big supporter of Gaussian process research, but at the same time, he was a bit of a contrarian. He wrote this essay in an edited book on neural nets where he has this quote: "How can Gaussian processes possibly replace neural nets? Have we thrown the baby out with the bathwater?" And what he meant was that when neural nets were being developed, they were envisaged as becoming intelligent agents that could discover interesting hidden representations in data. And while Gaussian processes had all of these nice statistical properties, they were also basically just smoothing devices. In which case, are we throwing the baby out with the bathwater and treating GPs as replacements for neural nets? The answer to this question is to build more expressive kernel functions which can discover interesting hidden representations in data. Although kernel methods and Gaussian processes and neural nets are somehow treated as competing approaches, they're often actually quite complementary. What we get with a neural net is a way to create highly adaptive basis functions which have very good inductive biases for a number of different application domains, such as image recognition. What we get through a kernel method in a Gaussian process is a way to have an infinite number of basis functions using a finite amount of computation. We can combine both of these properties together into approaches like deep kernel learning, where we have a neural net transforming the inputs of a base kernel to create a deep kernel, which is then jointly trained through the marginal likelihood of the Gaussian process as one model. So this gives us an infinite number of highly adaptive basis functions. Importantly, this is quite different than what we would get if we were to just use a neural net as a feature extractor, train the neural net, and then apply a GP to the result. Rather, deep kernel learning here is a one-step end-to-end procedure. It's a single model, and it's trained through the marginal likelihood objective. We can use Gaussian processes with deep kernels to do representation learning. In this example here, we have a Gaussian process with a deep kernel applied to the Olivetti faces problem, where we're considering faces with different orientation angles, and we're trying to predict the orientation angle for new faces. We can see, projecting what the model learns into 2 dimensions, that it discovers that faces with similar orientation angles, here each face is given by a line segment, and the orientation angle is given by the slope of that line segment, are clustered together, are similar in some way. We can also see this by visualizing the learned covariance matrices that we get, ordering the faces by orientation angle. In the left 2 panels, where we're using deep kernels, we see a pronounced diagonal band, which shows that the model learns that faces with similar orientation angles should be more correlated. This is non-Euclidean metric learning. In a sense, we can describe what a neural net is doing as learning a flexible non-Euclidean similarity metric for the data. In this sense, training a neural net is a lot like learning a kernel. In the far right panel, we have the entries of the trained Rbf kernel matrix, which we see are quite diffuse. Euclidean distance is just not a good proxy for similarity in this application. Looking at Euclidean distance of vectors of pixel intensities is not going to describe what we need to describe in order to solve this kind of representation learning problem very effectively. In this example, we're considering a discontinuous step function, and we see that a GP with a deep kernel in green here, the green shows the 95% credible set, describes that data very effectively. A GP with a spectral mixture kernel, a different type of kernel, is shown in red. It still fits the data all right, but it sort of oversmooths. We see a GP with an Rbf kernel fit in blue. From this perspective of a GP with an Rbf kernel, even though this is a flexible model, this kind of data is a very unlikely draw from the prior. We would have to sample for a very, very long time to see anything like this step function. And so since we can learn the noise here, the model is just saying, well, it's quite probable, if we believe the GP with the Rbf kernel, that this data is basically just noise and we'll have a very simple fit and a lot of uncertainty. So this example shows that Gaussian processes, for example, don't necessarily oversmooth the data or have trouble fitting discontinuous data. It totally depends on the kernel. And with a deep kernel, we can learn this kind of discontinuous step function data. Here we've applied a deep kernel structured with an LSTM network to an autonomous driving application where decision-making with predictive distributions is very important. We don't want to just know where lane boundaries might be, but we want to know, error bars on where these lane boundaries could be in making decisions. And we can see in the bottom row here that the predictive distributions do a good job of capturing the ground truth, and the point predictions are also better than the point predictions that what we get if we use the classic LSTM neural net. Conventionally, Gaussian processes have suffered from computational constraints, we need to solve a linear system involving our n by n covariance matrix for n training points, and also compute log determinants and derivatives of log determinants, which incurs naively an n-cubed computational cost, and exact Gaussian processes have often been intractable for problems with more than a few thousand points. Recently, by embracing advances in hardware, Krylov subspace methods have been developed that enable very scalable exact Gaussian processes through GPU acceleration and parallelization. And so in a sense, deep learning has progressed not only through advances in methodological design, but also by building algorithms that can really benefit from hardware acceleration, by thinking about how to benefit from systems. And GPyTorch, this package here, really is inspired by that approach in order to scale Gaussian processes with exact inference to very large problems. And when we do that, we can see that GPs with deep kernels often outperform standalone deep neural nets. Also, we can see that when we scale an exact Gaussian process to large problems, we can really realize the benefit of a non-parametric representation. As we add more and more data points, we can see that the error decreases very substantially. With a non-parametric method that has an infinite number of basis functions, the capacity of the model scales automatically with the amount of available information, unlike a parametric model, which is entirely determined by a finite number of parameters. Many approximate scalable inference techniques for Gaussian processes introduce low-rank kernel matrices. So this would apply to inducing point methods, stochastic variational inducing point methods, as well as random feature expansions, which basically turns the model into a parametric method. And we can see that on really large data sets, the gap between the scalable exact GPs and the approximate GPs is especially large. There are several other popular Gaussian process libraries, such as GPFlow, GPy, BowTorch for Bayesian optimization, that's black box optimization, automatic ML, hyperparameter tuning, A/B testing. And these libraries have different algorithmic foundations and use cases. There's also a lot of additional work on combining Gaussian processes and neural nets in various different ways. For example, Gaussian process regression networks and deep Gaussian processes build hierarchical models, replacing neurons in neural nets with Gaussian processes. Several other recent works have extended Radford-Neal's limits to multi-layer neural nets and other architectures like convolutional neural nets. And those limits are also very related to neural tangent kernels, which have been a very hot topic in deep learning recently, where we take infinite neural net limits and derive kernels, which have recently achieved fairly promising empirical results. Now, most of these kernels from infinite neural net limits have fixed covariance structure. And we described how training a neural net in many ways is like learning a kernel. That's what's doing the representation learning. And so bridging this gap and developing these infinite limits so that we can also do kernel learning, I think is a very exciting direction for future work in this space. Now, there are many ways to realize Bayesian principles in deep learning, in addition to the standard approach of marginalizing distributions over parameters in a neural net. In this part, we've really been considering how we can use neural nets to provide inductive biases for Gaussian processes for a Bayesian non-parametric approach to deep learning. In general, combining principles of Bayesian non-parametrics with deep learning is a very exciting area for future work. That's the end of part 2. In part 3, we'll be considering practical methods for Bayesian deep learning. Thanks for tuning in. We've just finished part 2, a function-space perspective of Bayesian machine learning and Bayesian deep learning. At this point, feel welcome to ask any questions, and I'll answer them as best I can. I'm mostly looking at questions in Zoom right now rather than Rocket Chat. So there's a question from Alex Immer. For finite width layers, how different are neural nets from Gaussian processes? And are there some architectures that do not converge to GPs? So I would say in many cases, the difference between the finite neural nets and the infinite limits is that the finite neural nets are often doing something like kernel learning, whereas when we look at the results of these infinite limits, we often get a fixed kernel. And I would say that kernel learning is really the way that kernel methods, like Gaussian processes, do representation learning. In the example we considered in part 2, we saw how, for example, a neural architecture could help in learning that faces with similar orientation angles are more correlated. Whereas if we were just using something like Euclidean distance of pixel intensities, that would be a pretty bad proxy of similarity for problems we're trying to solve. Whereas if we're considering maybe a low-dimensional regression problem, maybe Euclidean distance isn't really bad as a proxy for distance, because we might think that airline passenger numbers in 1960 are closer to passenger numbers in 1961, more correlated in some sense than they are to passenger numbers in 1950. Now, this doesn't have to be the case. So we can have sort of models with an infinite number of basis functions, infinite number of parameters that are also doing representation learning. So deep kernel learning is an example of being able to do that. Deep GPs also do that, as well as Gaussian process regression networks. And so, this distinction doesn't have to exist. And I think, unfortunately, sometimes historically, kernel methods and neural nets have been treated as competing approaches when they're actually quite complementary. Neural nets give us a way to create basis functions which are very adaptive and have very good inductive biases for several application domains, particularly image recognition and natural language processing. And kernel methods and GPs give us a really beautiful way of using an infinite number of basis functions, an infinite number of parameters with a finite amount of computation. And so there's no reason we can't have infinitely many highly adaptive basis functions and get the best of both worlds. And that's something that deep kernel learning is trying to achieve. Do the limits always have to be Gaussian processes? It depends. In many cases, when you take the infinite limits, when you have a distribution over parameters, you do get something like a Gaussian process through a central limit theorem argument. Okay. Other questions? In the deep kernel methods, is there any merit to being Bayesian over the parameters of the NN kernel? So there could be, yes. In principle, if we wanted to sort of follow a fully Bayesian approach, we would put a distribution over those parameters as well and marginalize them. I think until fairly recently, putting a distribution over all the parameters of a Bayesian neural net and then marginalizing it was just computationally a very challenging task. And it was sort of very hard to kind of do effectively. I think a lot has changed in that space over the last year, and we'll be talking about several methods in the next part that do perform this task very effectively. And so I think historically that's been something almost harder to do than using a Gaussian process with a deep kernel, where our uncertainty is in this sort of distribution over functions, and we're integrating that away, this infinite dimensional distribution over functions. I think in practice, though, that does give us a lot of what we would want from a Bayesian deep learning approach. So the credible sets, in my experience, using deep kernel learning tend to be fairly reliable. We don't seem to be overconfident, which is what we might expect if we were ignoring uncertainty too much. So we're conditioning on the hyperparameters of this deep kernel being known when in fact they wouldn't be entirely determined. So I think in practice, in my experience, it has been sufficient basically to have this hierarchical model where all of our uncertainty is coming from the Gaussian process, and then we have this deep kernel. But it could be fun and now possible to explore marginalizing a bunch of the parameters of this deep kernel as well, and it would be quite interesting, I think, to try to do that. So we have a question: how does training and evaluation in GPyTorch scale with the number of data points computationally? So GPyTorch is a library for scalable Gaussian processes, and it contains a variety of different algorithmic approaches to achieve scalability. If you want the fastest asymptotic scalability, methods like KISS-GP are very compelling, also known as SKI, structured kernel interpolation. These provide linear time scaling and training, ON, which is really the best asymptotic complexity that you could hope for if you were touching all the data points. If you and these methods can be very, very accurate. One sort of is somewhat of an advanced point, but one of the distinguishing features of GISGP/SCI is the ability to use many, many inducing points. And the accuracy of the approach is controlled by how many inducing points you have. So you can have even millions, billions of inducing points, and it doesn't necessarily cost you very much. So you can get both an asymptotically fast and highly accurate approximation using those approaches. The exact approaches in GPyTorch build on Krylov subspace methods like preconditioned linear conjugate gradients, and those have a complexity of n squared. However, you can actually deploy these approaches on problems with even millions of points through quite a lot of GPU parallelization. And so in a sense, a lot of the advances in deep learning have come about not just through algorithmic innovation, but through really developing approaches that embrace advances in hardware and systems. And perhaps this has been less the case in other areas of research. And so GPyTorch in part is an attempt to really embrace those advances and benefit from that kind of parallelization. So you just end up with a bunch of matrix multiplications in these algorithms, and matrix multiplies are kind of trivially parallelizable. And so we can just scale these exact methods to really huge problems, almost regardless of the n squared asymptotic complexity in many cases. And we found in this paper, exact GPs on 1 million data points, that in the large data regime, we could really benefit, especially from retaining the exact representation. So a lot of approximate procedures, in a sense, work by introducing some kind of low rank approximation to our covariance matrix, our kernel evaluated at all pairs of our input points. And this often turns our model back into a parametric model again, meaning that it's defined by a finite number of parameters. There are a finite number of basis functions. This would include, random kitchen sinks, things like this. And this means that often, you don't really, get to see the benefits of what we would sort of really sort of enjoy in using a fully non-parametric approach, where the capacity of the model is scaling automatically with the amount of available information. And in that paper, we could see that in those large data regimes, there was a particularly big gap between the exact and the approximate approaches. And that wasn't, known previously, because we couldn't actually scale the exact methods to problems of that size. So we have a question: what recent empirical results would you refer to as the most exciting, appealing applications of Gaussian processes or deep kernel learning compared to standard deep learning? Preferably more standard benchmarks, if any. So that I like the last part of that, the aside. In a sense, I mean, it's a common question, like what are the sort of success stories of Bayesian inference in machine learning? And I have two minds about this question. On the one hand, it sort of seems like, okay, well, representing epistemic uncertainty is crucial for decision making, and there will be a few application domains where that really stands out. On the other hand, it's sort of saying, what are the success stories of SGD or Atom? In a sense, it's kind of a generally useful thing to be doing, and it makes sense in almost every case, and I think especially in deep learning. And so what we're seeing now, which I think is fairly new over the last year or so, is just general improvements in both accuracy and calibration, predictive distributions, etc., on just a wide range of problems, including standard benchmarks like CFAR10, CFAR100, and so on. A few years ago, it was more common to see, well, on some UCI problems, we get better likelihood, better calibration, but CFAR10 still isn't great or whatever. That's all really changed, I think, recently. In many cases now, we can actually see a reasonable reduction in error, so like a 30% or so relative reduction in error by deploying a modern approximate Bayesian inference procedure in conjunction with a modern neural net architecture. There are a wide range of applications, and a lot of papers are now looking at ImageNet, which we'll consider in the next part, as well as CFAR10, CFAR100, SVHN, semi-supervised learning problems, few-shot problems, etc. There are a number of applications that have been coming up, I guess, quite regularly when one talks about Bayesian deep learning. So Jorn Gall has a Bayesian benchmarks, and his group has a Bayesian benchmarks project, and they consider diabetic retinopathy as an example. There are also, autonomous driving applications, image segmentation applications, and so on, which have received a reasonable amount of attention. And I'm happy to provide pointers to those works as well. Okay, so let's go on to part 3. If I missed your question, feel free to just ping me again, maybe privately on the chat, and I'll try to return to it in the next Q&A. And I'll be also attempting to answer questions in real time on the Rocket chat. So let's resume with part 3 now.